Standing waves occur when you shake a material to the point that the reflections of the wave line up with the outgoing wave and they form this pattern that oscillates in space. Any child with a skipping rope has done this pattern at some point. It occurs when you manage to get a wave to fit exactly in the space that you've got. You won't get this pattern forming unless you pick the correct frequency or wavelength. If you try any other frequency, you get chaos. Where the one bird is sitting, the two waves always completely destructively interfere at that one spot. The bird could sit. These are called nodes. On a single wave, a normal wave crosses zero here, goes up to a peak, goes down to a zero, and all the way up to another peak and back to zero. When a wave is in standing wave form, we have these three zero crossings that we call nodes now, and then there's an area in between called an antinode. The wave is not a crest, it's not a trough. It's oscillating rapidly between them. So it's going between total positive constructive interference, weakens, goes to zero, then it begins a phase of total constructive interference in the negative and goes back. So it's violently going up and down, but there's no sense of left or right travel on the wave. So we begin to talk about the parts of the wave now, not as crest and trough, but as antinode and nodes. Follow that one wave and you can see node, antinode, node, antinode, node. When a single wave is looked at, that is lambda. When it's in standing wave form, you can still see the individual wave that's making it up. So 1/2 of a wavelength on a regular wave is 0 to crest to 0. On a standing wave, it's from node to antinode to node. Look at the blue line. You can see it's still a single wave. So this is 1/2 lambda, and from the node to the antinode is 1/4 lambda. We can put the rope into many modes of resonance. You can shake it slowly and get this repetitive pattern that seems frozen in space. You can increase it to this one, and you can keep going and put as many of these node-antinode patterns as you want. If you try any rate of shaking in between those, the rope goes chaotic and you may find you feel the impulses hitting your hand, jerking your arm. It's very satisfying when you hit these resonant frequencies because it seems like you're doing very little work to get a very rewarding pattern on the rope, which this little girl seems to be finding far too much amusement in. There are two naming schemes for these resonant features. One of them is from music and one of them is from physics. In physics, we would call this the first, second, third, fourth resonance. In music, they will call it the fundamental, the first harmonic, the second harmonic, and the third harmonic. They may even call it overtones. But what you're looking at is multiples of a wave we can fit into this space on this condition. It starts with a node and it ends with a node because it's tied down at the end and it's tied down in the little girl's hand. There are several other ways of setting this wave up, but let's look at the one right now where it begins with a node and ends with a node. Now look at what she's holding. 0 to an antinode to a node. An entire wave goes from 0 to antinode to node to antinode to node. This is 1/2 of a wave. This harmonic fits an entire wave. This one fits one wave and another half. And this one, there's one wave and a second wave. You just simply have to count how many waves fit into the space as long as they fit the condition that it begins in a node and ends in a node. Looks even scarier now, but it's not hard at all. On this rope, fixed at both ends, the condition that will cause this standing wave to form is a wavelength of 1/2, 1, 1.5, or 2 waves can fit in that gap, and those special waves will oscillate back and forth and form this perfect standing wave. You can put any wavelength you want between the girl and the wall. They just won't form this beautiful standing pattern. Now, in math class, you were taught how to do sequences of numbers. Could you take a formula and create a sequence that when the number n goes from 1, 2, 3, that would generate these 4 numbers? If you can't do it, that's fine. But if you can do it, it'll come in handy next year. What happens if one end of the rope is not tied down? There are 2 ways of doing this. One way is she shakes the rope, keeping her hand very tight, not moving it up and down much at all, and the far end of the rope against the wall is tied on a loose string, so it's free to violently go up and down. Another way of doing it would be to tie the string to the wall at a fixed node, and she now violently moves her arm up and down, and she's created an antinode. Well, how much of a wave goes between a 0 and the first peak? If you look at the previous diagram, this is 1/4 of a wave. If you do this, you will definitely feel when you've hit the right frequency, because as you raise your arm, the rope wants to go with you, like it's anticipating. If you change your frequency, the rope will fight you like mad. Might even snap out of your hands if you try the wrong frequency. So let's take a look at what the conditions would be for a string that's tied down at one end and open at the other. In all situations, it now starts with a node and must end in a free vibration. So it starts at 1/4, and then we must add a half a wave in there, which means squeezing the wave smaller so more waves fit. So we reduce the wavelength. We pack in more. We can't add a half a wave or 6/10 of a wave or anything like that. We've got to shrink the wave so enough of a new wave fits that it's free at this antinode. Any other wavelength will work, but it will start to go chaotic. So in all these cases, it seems simple. We simply add another half wavelength in there. So from our fundamental, which is a 1/4 wavelength long, after that, each subsequent harmonic requires the addition of another half of a wave. So this sequence of numbers looks like this. It starts different, but it still advances by half a wavelength every time. Only the starting condition was different. When we do open end standing waves on both ends, her arm vibrates up and down, and the string is tied loosely over here. The only condition where we can fit an antinode and an antinode together is they must pass through the node. And this is 1/2 of a wave. So just like the first case, 1/2 of a wavelength is the first resonant length. And then it advances just like case number 1. Each time we shrink the wave size down. If we shrink the wave just enough so a whole nother half of a wave fits, we still make the condition that it ends in an antinode. And for the third time, all possible waves can go in this gap. But this is the magic wavelength that will form this standing pattern. And because it's forming a standing pattern, it gets very strong, it's being reinforced, it's a very noticeable, very strong pattern. So we keep squeezing in more waves. Now this may seem like an awful lot to look at, but it really isn't. If we put it all together, here are the three fundamental ways we can vibrate a rope. We can vibrate a rope where it's tied down at both ends, and it consists of a single half of a wave. We can tie it down in the middle and keep it free to vibrate on either end, and we also start with one half of a wave will fit in that space. Or we tie it down at one end, leave it loose at the other, and 1/4 of a wave fits into that space. This is the condition for a standing wave to form, this pattern. Any other wavelength will work, but it won't resonate. It won't reinforce itself and make a stable, standing structure. If I want to put this to a math formula, we can see that the first resonance is a 1/4 of a wavelength, then every next resonance adds a half more of a wave in the available space. We're not making the wave longer, we're making the wave shorter, so more of it fits in the space, but it must abide by the condition. You fit in more of the wave so it ends in a node or an antinode, depending on which of the three setups we're looking at. If you look at this one and this one, they both start off with 1/2 of a wave, and then we add another half of a wave for each resonant frequency. So the math series would be n is equal to 0 to 1 to 2, and it keeps on going, and these two formulas will tell you the total wavelength, the number of waves that fit into that space. You are better off drawing these three waves and using your intelligence to do this each and every time rather than memorize the formula. What instruments use these? For a string, the only possible use is the one on the left, a node at either end. There's no way to resonate a string like this and keep it under tension. There are a few musical instruments that let you bend a metal tab. This mode would be slapping a ruler on a desk where you pinch it down with your hand and go boing with the ruler. But no guitar can operate with one end of the string broken loose from the body of the guitar. So there are reed instruments, basically like the tines on a fork, or those little wind-up music boxes where the ballerina dances on the mirror and you hear the little tuning forks going pling, pling, pling. Those would be this mode of vibration, but not a string instrument. Let's take a look at a basic computation involving these standing waves. Suppose I tell you there's a guitar that has a string that's 55 centimeters in length and it's locked down at both ends, because that's what a guitar string is set up to be. So we know the string is 55 centimeters long. I'm telling you the speed of sound is 405 meters a second in that string. And I want you to tell me the frequency it will play at. Well, we can find the frequency using the universal wave equation here, but we need the wavelength. And what is this telling us? 1/4, or sorry, in this case, 1/2 of a wave fit into 55 centimeter space. This means the wave is twice as long as this. We are saying the length of the string is 1/2 lambda. Therefore, lambda is 2L, or 1.1 meter. Now we can use the universal wave equation and this guitar string should vibrate at that frequency. The most common mistake is this L equals 1/2 lambda. For some reason, most students will say, oh, if the length is 1/2 lambda and that's 55 centimeters, then I'll just divide by 2 to get my answer. I don't know why this formula causes that to happen, but when I say length is equal to 1/2 lambda, if it was any other formula, you'd immediately go lambda equals 2L. But for some reason, just this formula, 30 years of it, students will go, oh, if my length is 55 centimeter and that's 1/2 lambda, then lambda's 27.5. I don't know why this happens. Everyone does it. So just be careful of that. And what you have to realize is, just like Newton's law, that you should think of it as A equals F over M. This is another one that's saying, look, I told you the length, and it's lambda has to fit into that length. Don't sit there and try to manipulate the other way around. You'll have to think about it, but every time you set this one up, you have to say to yourself, if the length of the string is 1/2 lambda, then lambda is twice as long as the string. You got to really think about it, and it's childish math otherwise. So let's look at a real guitar in reverse. Okay, what is the length of a guitar string that plays a frequency of A440? That's just a fancy way of saying 440 hertz. So now I'm telling you the note, I'm telling you the speed, and you're going to compute lambda, and from that go backwards to the string length. Using the universal wave equation, the wavelength is 0.92 meters. Now, on a guitar string, node to node is the bridge here to the nut here, where the string is tied down at the bridge and the nut. Node to node is 1/2 of a wave. So 1/2 of a wave fits in the length of this string. So 1/2 of this fits the length of the string. 1/2 of 0.92 meters fits the string. Length of the string is 1/2 the wavelength. It's 46 centimeters. That's going backwards. These two are forward and reverse with this. I don't even want to call it a formula. It's just recognizing what it is you're looking at. It's like saying, what is the formula for measuring the height of my room from the sofa? Now, let's go backwards again. This is pretty common. If the guitar string in the previous example of 46 centimeters is now vibrated at its second resonant wavelength, what would the new frequency be? And in this case, we found an L in a previous problem. So it stays fixed as 46 centimeters, but you have managed to pluck the guitar string into its second resonant frequency, which is called a hammeron. And instead of vibrating like this, the guitar goes into a resonant frequency like this, and you get the node in the middle. Well, let's look at that now. Between the bridge and the nut, we are now fitting an entire wavelength in there. And we already know that it's 46 centimeters from here to here. So this one is pretty straightforward. The wavelength is exactly the string length in this one. The length of the string L is exactly lambda. They're both 46 centimeters in this mode. Pop it into the universal wave equation, and we get 880 hertz. Now, the prior vibration was at 440 or 380, something like that. There's always a little bit of drift in these formulas. And this has just about doubled it. Where the textbooks get singularly obnoxious is with these two setups here. You will find most of the textbooks now have finally smartened up and they're using the drawings on the left. The drawings on the right still show up in older textbooks, and checking on the internet, I've watched now these drawings are getting progressively harder to find. They're not wrong, they're just stupid. This is telling you in the same length of a pipe or a string. It's a string when it's on a guitar. If it's a pipe, this is air moving like this. This means that on a guitar or on a flute or any instrument that's using a standing wave, I can blow harder on a flute or pluck harder on a string instrument, and in the same available space, I can cram more waves. On a flute, this means the harder you blow, the higher the sounds. And I'm going to take the parent's nightmare called a recorder, the most awful musical instrument ever made, and I'm going to show you. That's the fundamental. Then I jumped up to the middle drawing. And that was the third harmonic. So as I blew, the same fingering made the flute or recorder or devil's whistle jump from this note to this note to this note without changing my fingering. That's what real musical instruments do. Some physics teacher a long time ago decided this was a good way to draw it. Who would do this? You're like, hey, Billy Bob, you know that guitar of yours? I made one 3 times longer. You can't even reach the end of it. It's so long, and it plays exactly like yours. Why didn't you make it? Because mine's bigger. Costs 3 times as much, and there ain't nobody that can reach the full length of this thing. This would be like, hey, you know that flute of yours that like you can barely get your fingers on? I've made a flute 6 feet long. There isn't a human on the planet that can play it. Well, what's special about your flute? Nothing. It plays the same note your flute does. Why on earth would you double the length, or not quite double, but it's actually more, right? Look at that. It's 1/4 of a wave long. Now you make it 3/4 of a wave long. For what reason? It's making the same wavelength. So this one showed up in the physics textbook somewhere, and you're like, no, we don't make musical instruments that way. What instrument operates in a mode like this that's not, because string instruments can't? Wind instruments. So the wind instruments that end in a mouthpiece that you shove in your mouth, clarinet, saxophone, tuba, where there's no upper hole, you're dealing with a node and an antinode wherever the hole is open. So the lowest note on a clarinet would fit from here to the bottom. Now, the clarinet is 66 centimeters long. That's an actual clarinet. And if we play the lowest possible note on a B-flat clarinet, it's 146.83 hertz. You can look it up. I'm not lying. On a really warm day, the speed of sound would be 350. What is lambda? And solve for the length of the pipe. Well, it's real simple. Lambda solves to 2.38 meters. That is not the length of the pipe. What it's saying is one wavelength is 2.38 meters. But in the clarinet, on its fundamental tone, only 1/4 of that fits into the pipe. So we have to divide by 4. We get 59 centimeters is the position of the lowest note on this clarinet. And if you look from mouth to the end is 66, and there's the hole for the lowest note right there. So it's pretty close. Now, how can air move like this? It does not. A string vibrates up and down, but this simply means the air is sitting still here, and here the air is alternating between high pressure and low pressure. So it's a pressure graph now, not an actual drawing of the air waving up and down. Strings physically shake like this. This is just a plot of air pressure in a wind instrument. Here's another one. The recorder I just played. The lowest note it can play, a god-awful note from the pits of hell. That's 551 hertz, measured it with my cell phone. Speed of sound in my room is 333 meters a second, half the number of the beast. So I measured that. Yes, I can measure the speed of sound in my room. Can't you? You should. It's the newest thing. And I measured exactly 24 centimeters between this hellhole and that hellhole on the recorder. Well, it's open at both ends. How can you tell? Look, there's an opening right there that my mouth doesn't cover. Though I did try a few times as a kid to see what would happen if you shove the recorder deep in your mouth and try to get your lips over this hole, and it can make you vomit. Don't do that with a recorder. No, like plowing it into your mouth. So the recorder must end in an antinode. There'll be a node somewhere in the middle and another antinode where I opened the hole. And I measured 24 centimeters here. So what does that do for us? Well, 24 centimeters is half a wavelength, because this is half a wave. So if half a wave is in 24 centimeters, then 48 centimeters is a full wave. When I use the universal wave equation and solve, I get 693 hertz versus 551. And I darn well know this number is accurate because I measured it. So why did it come out so high? Well, these instruments aren't perfectly represented by this. The fact is, even though air is getting out of the hole here, there's still some blockage with this rest of the 4 centimeters. So if I add those in, and I add those extra 4 centimeters on, the predicted frequency has dropped a bit. Whole 100 hertz, that's quite a bit. Definitely noticeable. Anybody could hear that. And so it's getting closer. And then I'm thinking, well, is the air truly like open here? Or is it starting to stifle off again or something in this last bit? So if I add the entire length of the recorder together, the predicted frequency drops to 555, which is getting darn bloody close to what I measured with my cell phone. So the formula does work, but if you were an instrument maker, like every formula I've taught you, there is going to be a massive amount of re-engineering and putting other things into the formula to make it work properly for musical instruments. And that's why real flutes, not the recorder, have all sorts of little secondary openings and all sorts of holes you wouldn't predict. Even these like double drill holes. There's all sorts of little fine tuning things they put into it, because this rule here, this little universal wave equation, needs other terms to deal with a real world instrument. So it will get close, but not perfectly. Now, a person that studies instrument making won't necessarily learn all the correct formulas. They will learn rule of thumbs like, oh, well, you can drill a hole here to make it play that note, but you got to make the hole a little bit smaller or it sounds like hell. And they've just adjusted it sort of by ear over the centuries. And one thing about hearing is your hearing picks out a sour note really fast. So there's a level of tradition behind these instruments where the physics might get a little too complicated to actually predict.